week of the first channel lecture series. And today we have with us Dr. Rahul Dalal. And I now request Surya to chair this session.
Uh, okay, yeah. So yeah, it's a pleasure to invite Rahul. So he's a postdoc at Johns Hopkins. He got his PhD from Berkeley, and he was an undergrad at Harvard. So this is his first talk on trace formulae, and automorphic representations. Today he'll be talking about all the trace formula and its applications. Yeah, I'll hand it over to Rahul.
Yeah. Thanks for the introduction and thanks for the invitation. I guess it's a big honor to be speaking in this, and the previous talks have been very good, so it's a little bit intimidating, and I hope I can keep up the quality. So let me first start with a little note on these slides. So I think it's useful to sort of like color code a few things in the slides. So there are going to be some things that are going to be highlighted in gray, and those are basically technical details that get in the way of conceptual understanding of the subject if you haven't seen them before. So if you're new to the subject, feel free to ignore anything in gray. I'm also going to put some things in orange, and these are sort of very important key concepts that most of them have been touched on in previous talks. I will try not to go over them in much detail in this talk. I'll just re-explain them sort of intuitively and imprecisely, and that's just for time constraints. So, okay, so that's the orange and gray. So let's begin with the talk then. Okay, so previously what happened is, well, you guys were introduced to this thing called an automorphic representation, and we heard a lot of justifications for why they're interesting, all these very interesting and important math problems that they help us solve. So for example, through the Langland's conjectures, they tell us a lot about arithmetic objects. For example, we had to talk about the Sato-Tate conjecture and how that links to automorphic representations. They also give us a lot of information about the cohomology of locally symmetric spaces. So there are a bunch of other things, but these are the two that we've seen, and hopefully this is enough justification why these are things that we should care about. So however, there's a problem. The problem is that these automorphic representations, they end up being pretty scary, complicated objects. So specifically, the functions that make them up are like very special solutions to complicated partial differential equations on very high dimensional spaces. And it's not just any solution. You have to find a solution where things perfectly line up so that things decay fast enough, and it ends up being very complicated. And maybe just to emphasize how complicated these objects are, when the tools that we know how to study them with don't perfectly line up, there's some very basic counting or existence questions that are open. So for example, well, I'm going to use some of the language here, but I don't think anyone knows how to write down a non-self-dual level 1 cuspidal automorphic representation on even just GL3. And they're like very simple problems that are open on GL2 even. So I don't think there's a known asymptotic formula for how many weight one modular forms there are of level less than or equal to n. So these are just two problems where the tools that we have just don't apply, and they sound like things that people should know, and it's just completely open. So, well, what's going to happen in this talk? Well, we're not going to talk about these problems. What we're going to do is, because these are scary, complicated objects, we're going to talk about one particular tool that's very useful for studying automorphic representations. And this particular tool is called the Arthur-Selberg trace formula. So of course, there are a lot of other tools, and we've seen some of these in the talks before. They're theta lifts, they're converse theorems, they're other things. And each of these tools is very powerful, can give lots of results. And well, the more of them you know, the better. Okay, so now that we're sort of situated and how this talk fits into everything, let's start with our perspective on what an automorphic representation is. So in this talk, and with the trace formula in general, it's most convenient to use the full abstract Adelic language for describing automorphic representations. So here's the sort of working definition that we're going to use. So we're going to pick some reductive group over some number field, and we'll call that group G. Then a discrete automorphic representation for G is an irreducible subrepresentation of this particular space of L2 functions. So let's just review what all these words mean, and maybe let's talk about how this relates to maybe the more, just review again how this relates to the more classical perspective. So first of all, what's a reductive group? Well, a reductive group is basically a matrix group such that all the representation theory results you learned in a Lie groups class apply. So you can just pick one of your favorite matrix groups, GLN, SLN, unitary groups, orthogonal groups, symplectic groups. And basically the point is this matrix group is defined based on algebraic equations. So you can figure out what the group is over any sort of ring, and you just look at the solutions to the algebraic equations that define the conditions on the matrices you need to have. So what is this L2 space? Well, this L2 space, well, okay, so you take matrices satisfying those conditions with coordinates in the adels of this number field, and you mod out by matrices satisfying the conditions with coordinates in the number field. And the point is that this thing over here, this is a topological group that's nice enough. So you have some kind of invariant measure here. So you can talk about L2 functions with respect to this measure. And what you can do is then you can talk about these functions under translation. So it's very important that we do this specific translation operation. Somehow it kind of, in this subject, you have to be a little bit paranoid, and you have to be very careful about which side you're multiplying on and whether you're doing inverses or not inverse. And this will come up later, so remember this. And so this quotient, again, it's a little weird, but it's sort of it's an abstract tool. And well, if you've seen the classical perspective on automorphic representations, what happens is you look at basically these real matrix groups mod arithmetic lattices. And what this GA mod GF is it's a limit of these real matrix groups over sort of all the arithmetic lattices. So this is basically a technical object that lets us talk about every level at the same time. So functions on this are functions of any particular level. Okay, so that's the L2 space. Now let's continue. So what does subrepresentation mean? Well, of course, this L2 space, this is infinite dimensional. So you don't really know that any unitary representation actually decomposes as a direct sum of irreducible representations. Just like L2 of R doesn't give you a direct sum. So we basically add this weasel word in, discrete, and discrete just tells us that we can literally think of it as a subrepresentation. So there is a definition for non-discrete, but we're not going to go into that. That's sort of one of the technicalities that maybe we don't need to go into today. Okay, so that's great. So next, well, the applications of automorphic representations usually depend on one of two key questions. So the first one is, well, this L2 space is a representation of G of the adels, and it breaks out. So these discrete ones are subrepresentations. These are irreducible unitary representations. And of course, not every irreducible unitary representation of G of the adels is going to live inside this L2 space. So the first question that's usually important is which representations actually appear in L2. So the other one is there's certain integrals of the functions in the representation that you can take called period integrals, and these give you information about L functions. So lots of other applications depend on these. So today we're just going to focus on the first application, just because this is the one that the Arthur-Selberg trace formula is very suited towards giving information about. I think later in the semester, there are going to be talks on the relative trace formula, and we've seen some talks on L functions already, and those tools are very good for talking about the second key question. Okay, so that's the perspective that we're going to take on automorphic representations. Does anyone have any questions at this point? Okay, so let me move on then. Okay, So this is our perspective. Let me maybe give a little bit more detail on what exactly I mean by this first key question. So as a first result, so basically, so the automorphic representation is a representation of G of the Adels. And G of the Adels, what factors as almost basically a product over places of the number field of G of the localization at that place. So an automorphic representation is an irreducible representation. And if you have an irreducible representation of a product of groups, well, that should just be the tensor product of irreducible representations of the individual groups. So up to some technicalities, because it's an infinite product, this basically works out for automorphic representations. And the important technicality that's going to come up later is that well, these components, almost all of them have to satisfy a particular condition that they're unramified. So what does unramified mean? Well, unramified means that almost all of these GFFVs sort of contain a KV, and this is basically a maximal compact subgroup. And well, pi v needs to have a fixed point with respect to kv. So that's what this unramified condition means. So if you sort of remember how the Adels are defined as some kind of restricted direct product with respect to maximal compacts, you should sort of expect that something's going on with the maximal compact subgroups here. So that's sort of the important technicality here. And there's a kind of these local components over the places VFF. They let you relate the Dalek perspective to the more classical perspective. So basically what's going to happen is that, well, okay, so these local places, they're infinite places and finite places. And the components at the infinite places, they're basically going to tell you what the qualitative type of automorphic representation is that you're looking at. So basically, whether it's a modular or a Moss form for GL2, what its weight is, things like that. And what the finite components are going to tell you, they're basically going to tell you the sort of level of the automorphic representation, and they're going to give you a generalization of the information of what the Hecke eigenvalues of a modular form are. So in ramified, and there's this extra detail that if the component at V is unramified, that sort of means you should think of that as like V not dividing the level. So this is just a little bit more about how to translate. So the key question, which representations of GFA actually appear inside L2? You can think of that as which combinations of pi V actually appear in L2. So in the modular form setting, that's basically asking, like, you fix the weight of a modular form, you fix all the Hecke eigenvalues, and does that actually give you a modular form or not? So this is the thing that's important in a lot of applications. Okay, so that's a little bit more on our key question. Now let's talk about where the trace formula comes in. So we want to try to answer this key question, and we're going to start with the piece of representation theoretic intuition that maybe you learn when you first start studying representations of finite groups. And that piece of intuition is that instead of worrying about a representation, if you want to answer a lot of questions about the representation, you can think about the trace character of the representation instead. So for a representation of a finite group, if you just know the trace of the representation against every element of the group, that basically encodes almost all of the information that you would care about. So what is the Arthur-Selberg trace formula? Well, what it's supposed to be is a formula. Well, it's maybe not exactly a formula, but for something like the trace character of this entire L2 space as a representation. So in particular, maybe you can expect that like finite groups, that when you know the trace character, you know how the representation breaks up into irreducibles. Of course, this is not going to work out perfectly in this case, but it's sort of the heuristic motivation that that motivates the trace formula. So basically this irreducible makeup, this is our key question, right? which combinations of pi v live inside here, are the irreducibles that live inside here. So this is all great for heuristics, but they've actually been worked out. So the heuristics have been worked out rigorously and have given a lot of good applications of the trace formula. And the applications of the trace formula tend to fall into two main classes. So first, well, you can look at the trace against L2 of two different groups, and you can compare the formulas for their traces. And then maybe you can do some abstract things, and you can say that like there's a piece of the formula on one side that also appears on the other side. And this basically gives you a lot of information for cases of Langland's functoriality that's come up in previous talks. So basically transfers of representations from groups to other groups. And there's sort of three cases of this Langland's functoriality that maybe are the known applications so far. People have talked about base change. There's something called endoscopic lifting, and there's something called the endoscopic classification. So these applications are sort of maybe the most well-known, but they end up being pretty difficult conceptually, and they require very sophisticated versions of the trace formula. So in this talk, instead, we're going to focus on different applications where you look at sort of special cases of modular forms. You try to count how many there are, or maybe you try to understand average statistics of these modular forms. Like maybe there's some parameter and you want to know the distribution of this parameter over modular forms satisfying some property. So this application is a little bit more conceptually simple, and I think it gives a sort of a good sense of what the trace formula is and how you can use it. So this is what we're going to focus on today. Okay, so are there any questions at this point? Okay, so let's move on to basically more heuristics about how the trace formula works. So the trace formula is one of these things that there's a thing it's trying to be. It's trying to be a formula for this trace character, and there's a thing that it actually ends up being once you put in all the technical details. And it's very easy to get pretty lost if you don't have the heuristic in your head of what it's trying to be. So we're going to spend a lot of time on this heuristic of what the trace formula is trying to be. And if you assume that it's what it's trying to be, how you can use that to solve these counting problems. And then after that, we're going to talk about all the technical details that come in. So let's start with these heuristics. So first of all, we have to talk about what trace character means for an infinite dimensional representation, right? Because if you have an infinite dimensional representation and you take an element in the group and you look at the action on that representation and you try to take the trace, well, that trace might not be finite. So basically what you end up doing instead is instead of considering traces of single elements of the group, you consider sort of average traces averaged over the group depending on a function on the group. So what we can do is if we have a nice enough function f on g, we can define something called the convolution operator, which I'll be denoting by rf. And that's going to go from pi to pi. And what it's going to do is it's going to take v to the integral over g of f of g times g acting on v dg. So again, what is this dg? Well, this dg is a translation invariant measure called the Haar measure. So it's just a natural thing to use when you're averaging over a group. And again, so the intuition of this, you should think of it as sort of a not translation by a single element, but a sort of smeared out translation. So you're looking at translation by a bunch of different elements and you're averaging it out. And the way you average, you determine that by the weights given by this function f. So the point is you hope that if this function is nice enough, then this RF is actually something that has a finite trace. So the trace character, we don't think of it as a function from the group to sort of the complex numbers. We think of it as a measure or a complex valued measure that it will denote by trace sub pi, and that takes a function f to the trace against pi of r of f. And of course, there's serious analysis issues when you write this down. You have to make sure that what space of functions and what space of functions actually gives you something finite. Maybe you might be interested in how regular the measure is. And well, for irreducible representations, there's a very good theory developed by Harishchandra. And well, actually, this is where things become a heuristic. This existence is not actually true for all of L2. And that's why this entire section is going to be heuristic, and we're going to have to correct everything with technical details later. Okay, so that's our trace character. Now let's talk about what a formula for this trace character might look like. Again, we're just working in the heuristic world again. Okay, so on one side, we have a kind of spectral expansion of this trace character. And the spectral expansion is going to describe for us how knowing traces tells us about the components, the local factors of the irreducible constituents of L2 space. Okay, so this one is not too complicated. They're basically two steps. So first, well, because we're in heuristic world, you just assume that your L2 space decomposes as a direct sum of irreducibles. Then what's going to happen, just the way traces work, the trace against the full L2 space is just going to be the sum of the traces against each of the irreducible subrepresentations. Okay, so that's great. The next thing is that, okay, so again, we have this factorization of each irreducible subrepresentation as a tensor product of these local factors. So what we're going to do is then if our function factors as a product of local functions, so remember f is a function on g of a, so each of these is going to be a function on g of fv. So it's just a function on a product. A special kind of function on a product is a product of functions on sorry, is someone asking a question or? Okay, well, I'll go on. Yeah. So a function on a product, we're just looking at it. Sorry? Okay, should I continue? Okay. So yeah, the function on the product is just a product of functions on each of the factors. And well, it turns out because of the way traces work on tensor products, then you get a factorization of this trace against pi into a product of traces against pi v. So this is sort of the full sort of spectral expansion that we're going to use, that the trace against all of L2, well, it has all the information of the traces against all the local components of each of these irreducible subrepresentations. Okay, so that's great. The next piece is, well, so that's how the trace tells us about the local constituents. Now we actually need a formula for computing the trace. And the way we're going to get this formula is we're going to interpret this RF as a integral kernel operator. And there's a sort of abstract functional analysis theory that lets us compute traces of these things called integral kernel operators. So let's describe that theory. So we're going to take some L2 space, L2 of x, and we're going to consider R an operator on this L2 space defined by when you take R of a function phi and you evaluate that function on a point x, you get this particular integral of some two variable function kr of xy integrated against phi. Okay. So the key point is that if kr is nice enough, then the trace against L2 of the operator R is just going to be the integral along the diagonal of this function kr. So the intuition here is that this formula over here should look a lot like the formula for matrix multiplication, except the sum over the indices of the matrix is replaced by the by an integral over the space. So what you're doing is you're basically thinking of this operator as a infinity by infinity matrix and represented in a basis of sort of delta functions at every point in the space x. And all this is saying is this is just an integral version of the trace of a matrix as a sum over the diagonal entries of a matrix. So this is the formula that we're going to use to actually get another way to look at the trace. Okay, so if we're going to do this, the first thing we have to do is we have to take this convolution operator. We pick a phi inside this L2 space. Sorry, this is a typo. So we want phi is just maybe a function on the adelic points of the group. And this convolution operator is going to act on the L2 space. And we want to see if we can write it as a kernel operator. So let's try doing that. So we'll start. So we take a function. Oh, come on. So this is f. So yeah, so this is f. This is our okay, well, this is going to be wrong on every slide. And then phi is going to be our function inside the L2 space. Okay, so we're going to take this function phi inside the L2 space. We're going to apply this convolution operator to it, and we're going to evaluate at a point h. And remembering the way the group elements act on phi, we're going to get this particular, this is just writing out all the definitions of what this means. Okay, so if you remember the formula for a kernel operator, basically this is almost good, except for two things. The first thing is that there's an h inside the phi. So we first have to get rid of that h. And this is how we're going to get rid of the h. Because our measure is translation invariant, we can just make a change of variables. G goes to h inverse g. And now there's no longer an h inside the phi. The h is just inside the f. So at this point, we've written this RF as a kernel operator, but the kernel operator is on G. It's not on GA mod GF. So I'm sorry, I'm just using some shorthand here just to make sure that just to keep this short. So just as always, G is going to be GA and gamma is going to be GF, just to keep things simple. Right, so we need this to be an integral over gamma mod G instead of just an integral over G. So how are we going to do that? Well, we're just going to break this integral over G into a sum over gamma and then an integral over gamma mod G. So we just do this. We just insert another variable in our integration. And we can do it this way. And then basically what happens is that we need to remember that phi was a function on G mod gamma. And because phi is a function on G mod gamma, this blue factor of gamma inside the phi doesn't matter. So we can basically factor the phi out of the inner sum, and we get this final formula here. And basically what this tells us is that this is our KRF. And so that's how we interpret this convolution operator as a kernel operator. Okay, so now that we've done this, let's integrate it along the diagonal and see what kind of formula we might expect. Okay, so again, we're going to use this shorthand that gamma is GF, G is GA, and we're just going to work heuristically, so we're not going to worry about convergence issues. So the trace against RF is the integral of this kernel against gamma mod G along the diagonal. So we substitute in our formula for the kernel. And the first thing we notice is that, we're conjugating gamma. So this inner sum over gamma, we can break it up kind of into a sum over conjugacy classes and then a sum over each conjugacy orbit. So this is sort of the key trick in this derivation. We break up this inner sum. And so what's going on here? Well, so this is the set of conjugacy classes. And this notation here, gamma sub little gamma, this is the centralizer of little gamma and big gamma. So all the this is how we conjugate. This is how we parameterize a conjugacy class, right? You just you look at the group mod the centralizer and all the conjugates by the group mod the centralizer. That gives you the entire conjugacy class, and it gives you every point in the conjugacy class exactly once. So all we're doing is we're just reindexing the sum, breaking it up into two pieces. Okay, so now we can do something interesting. So the point is this inner sum over gamma mod the centralizer. This inner sum is gamma invariant, right? So if you switch your g by if you change your variable g by something in gamma, it doesn't change the total value of this inner sum. So that basically allows us to swap the integral and the outer sum. So we can get this formula here. So the sum over conjugacy classes can actually come out of the integral. So these two steps are sort of the key trick that we can take the sum over gamma, we can break off a sum into conjugacy classes, and that sum over conjugacy classes actually comes out of the integral. And then once we have this, we can just keep simplifying and we're sort of home free. So what happens is that this inner integral and this inner sum together, they're basically an integral over G mod the centralizer of gamma inside big gamma. So what we can do is we can break up that integral in a different way. Instead of being an integral over a sum, we can break it up into two different integrals. And the reason why we're going to do that is this integrand over here is independent of h because h lives in the centralizer of little gamma. So we can just evaluate the inner integral as just a volume, and we're left with this formula over here. So this is the heuristic of sort of what we should expect of what the trace against the L2 space should look like. It should look like the sum over conjugacy classes inside gamma of this volume times this integral over a conjugation orbit. So let's discuss this in a little detail just as a summary. So the full heuristic formula, and now we're just going to use the full notation with g of the Adels and g of f. We have some f that factors as a product of fv, and we get that the sum of traces is equal to this thing called the geometric side. So again, there are three key pieces here. There's a sum over rational conjugacy classes. There's a volume, and if you look at the specific volume, you take the centralizer of gamma, and you're looking at the adelic points mod the rational point. So this is kind of like a Tamagawa number. And then there's an orbital integral. So if you know how to parameterize rational conjugacy classes, compute these volumes, and compute the orbital integrals, then heuristically, you should be able to compute these traces. Now, practically what ends up happening is that this red and this blue are usually not too much of a problem. Parameterizing rational conjugacy classes, well, this is very approximately sort of something like characteristic polynomials. Characteristic polynomials, there's a way to generalize them to other reductive groups, and it's not literally true that you get rational conjugacy classes out of that. You get something called stable conjugacy classes instead, but well, there are techniques to go back and forth between the two. So this red sum is usually not too bad. These volume terms, well, yeah, so these are these adelic quotients. They're just these Tamagawa numbers, which I guess there's a formula for them. There's a Coltwood's formula for the Tamagawa number. And so basically what happens is that in practical use, these orbital integrals are the hard part. So when you actually want to compute something with the trace formula, what ends up happening is that the barrier becomes computing these orbital integrals, and as much information as you can get on the orbital integral, that's as much information as you get on the traces. Okay, so that sort of finishes our heuristic about how the trace formula might work. So next we'll sort of continue this heuristic, and we'll assume that we have this beautiful great trace formula, and we're going to try to figure out how we might count something with it. Okay, so before we start that, are there any questions? Okay, so let's talk about how we might use this to count. Okay, so what's sort of the most basic sort of like, this is going to be a little bit abstract, but what's sort of the most basic counting problem we can think of? Well, we can look at the set of automorphic representations of a group G, and we can try to count how many automorphic representations satisfy some condition CV at each place pi v. So this pi, right? We recall this pi, right? It's this tensor product of pi v. So we can ask how many satisfy that the pi v satisfies condition CV. Okay. So because remember in our factorization we have this technical condition that pi v needs to be ramified at almost all places. So if we want a non-zero count, we should our condition CV at all but finitely many places should be that this pi v is unramified. And again, unramified, it means it has a fixed vector under a maximal compact. So basically we're not, when we're doing this counting problem, the key point is there's secretly only finitely many conditions, right? You're picking finitely many CV that aren't this like default condition, and all the other CV are this default condition, which you can just think of it as there's one condition that pi v isn't ramified at all places except these, and at these places you have another condition at pi v. So this problem isn't as crazy as it looks. Okay. So basically what we want to do, the way we would do this, is we would try to find test functions fv at each place v, such that the trace against pi v if fv is just 1 if the condition of pi v is true, and 0 if the condition of pi v is false. So if we can find these conditions, then we can find these if we can find these test functions, then basically what's going to happen is that the trace against L2 of this product of all these FVs, if we look at the spectral expansion or heuristic spectral expansion, we should expect this trace to be related to the count of automorphic representations such that this condition CV is true for all V, right? I mean, what's this going to be? This is going to be the sum over automorphic representations of the product of trace against pi v of fv. So you can see here that the only terms that are going to survive are the terms where this trace is 1, where the condition CV is actually true. And the terms that survive for each pi, you're just going to get 1. It's just going to be a product of a bunch of 1s. So it's really going to give you the exact count. So this is how we use the trace formula to count something. I think it'll help to give sort of a more explicit example. And the more explicit example, it's not going to be literally counting automorphic representations. It's going to be a slight variant. So what we're going to do is we're going to try to think about how we might use this heuristic trace formula to count the dimension of the space of weight, k-level, and modular forms. So now we sort of have to pass through this dictionary again between the classical perspective of modular forms and the adelic perspective. So in this dictionary, modular forms correspond to automorphic representations where the number field F is the rational numbers and the group is GL2. So what does level n mean? Well, the level n condition for modular forms, it corresponds to a particular level subgroup inside GL2 of basically the finite adels. So this level subgroup, this is a product over all primes of some level subgroup K sub P. Maybe we want to you'll maybe write this as P to the power, where that's the power that divides n. So we're just going to shorthand it as living inside A away from infinity, the finite adels instead of the product over all it's the same thing. It's just different notation. And the point is, well, level n corresponds to some level subgroup, right? Some arithmetic lattice gamma sub n. And the way this level subgroup is defined is that what you do is that, well, this GQ kind of diagonally embeds inside GA infinity. So what you can do is you can take the intersection of Kn with this diagonal embedding. That gives you a subgroup of GQ, and the subgroup of GQ lives inside GFR. And that's supposed to be our arithmetic lattice gamma sub n. So again, this is just a little bit more on the translation. So what's going to happen next is that as part of this translation, so every classical weight K modular form is going to produce an automorphic representation, but it's not going to produce any automorphic representation. It's going to produce an automorphic representation where the infinite component is restricted in some special way. And the infinite component needs to be specifically equal to a particular representation of GL2R called that I'll denote by pi sub k. And that's something called the weight K discrete series. And I think these have also appeared in a previous talk. So that, if you have a classical modular form, that gives you an adelic automorphic representation. And you can also kind of go the other way. So if you have an adelic automorphic representation, the vector space of level and modular forms associated to it is, well, what you do is you take the away from infinity components of the automorphic representation. This is going to be a representation of G away from infinity. And you look at the Kn fixed points. So this lets you translate back and forth. And the upshot is that what's the dimension of the space of weight K level and modular forms? Well, that's going to be basically you look at all automorphic representations of GL2. You look at the ones where the infinite component is equal to this weight K discrete series. And for each of those, you sum the dimension of the away from infinity components and then the Kn fixed points. So this is what we're trying to count when we're trying to count weight K level and modular forms. Okay, so now we know what we're trying to count. How do we get our test functions? Well, the first thing we're going to do is magically, by sort of some harmonic analysis arguments on GL2 of R, there's a function called a pseudo coefficient. And the pseudo coefficient, it's almost the matrix coefficient for a finite dimensional representation. And it turns out it has a very special property that the trace against any irreducible representation of G of GL2R against a pseudo coefficient is just going to exactly tell you whether this representation is equal to the weight K discrete series or not. There's a little technicality when K equals 2, but for all the other K, it's fine. Okay, so that just comes from some abstract considerations. We get this test function at infinity for free. What are we going to do away from infinity? Well, if we basically take the indicator function of this level subgroup K sub n and we normalize it by the volume, then you can check that the convolution operator against them is the projection from pi away from infinity to the fixed points. So if it's this projection, then, well, how do you compute the trace of the projection? The trace against pi away from infinity of f away from infinity is just going to equal the dimension of pi away from infinity fixed points, right? That's just how the trace of projection operators work. So basically all we have to do is we just have to set f equals f at infinity and f away from infinity. And well, okay, this is the test function we use. That's not all we have to do. We have to actually compute the geometric side also. But you can see sort of how if you can compute the geometric side, and in particular, if you can say something about these orbital integrals, then you can get a formula. And you can get, or maybe some partial information about how many modular forms of weight K and level n there are. So of course, the point of this is that this argument, this heuristic, is not just special to GL2. You can also do things on other groups. And similar methods to this should basically work in great generality, as long as all the heuristics that we had here were precise. Okay, so there's one last heuristic thing that I've sort of been hiding again, and that's computing the geometric side. And again, in particular, working with these orbital integrals. So I'm not going to say how to deal with these orbital integrals in general, because there's sort of no good way to do it, and you just sort of have to find some particular hack for the particular problem you're working with. But well, one thing you can do is that if you don't worry about an exact formula and you only worry about asymptotic formulas, then a lot of the most complicated orbital integrals will go away. So let's just recall what the geometric side looks like. Again, it's a sum of irrational conjugacy classes of this volume factor times this orbital integral. So as we're doing an asymptotic, what's happening is this function f is changing, right? So remember this f, maybe in our modular form case, it was the pseudo coefficient times this indicator function. So we want to figure out what happens to this entire term as f changes. So basically we need to focus on what are the asymptotics of this as f changes. Okay, so what's going on as f changes? Well, basically, as your level n is getting bigger, your arithmetic lattice is getting smaller. So basically, the subgroup Kn needs to be getting smaller. So as n is going to infinity, the support of this Kn is getting smaller and smaller. In addition, as k is going to infinity, I said that this pseudo coefficient is sort of like a matrix coefficient of a finite dimensional irreducible representation. And taking k to infinity is kind of like taking the highest weight to infinity. So the pseudo coefficient is going to oscillate more and more rapidly as k goes to infinity. So the upshot of both these asymptotic expectations is that you should sort of expect that these orbital integrals are going to decay at a rate proportional to the dimension of the conjugation orbit. So basically, if you have some ball in some high dimensional space, and you're integrating some smaller dimensional space, and then you're letting the ball shrink, well, you should expect that the rate of the integral on the smaller dimensional space should decay sort of like the dimension of the smaller dimensional space. That should be like the exponent on the decay, right? And there's a similar sort of like Fourier analysis thing that if you have a rapidly oscillating thing and it's oscillating more and more rapidly, then it cancels more and more, and you get like more cancellations the more dimensions in your integral you have. So you should expect that these orbital integrals decay at a rate proportional to the dimension of the orbit. And that's really great, right? Because which conjugacy classes have the smallest dimensional conjugation orbits? These are the central conjugacy classes, where the conjugation orbits are literally just the point. So what you should expect is that in any asymptotic, the terms on the geometric side for central gamma are going to dominate. And now for central gamma, this orbital integral, it isn't an integral anymore, right? It's just evaluation of the function at a point. So suddenly when you're doing this asymptotic, as long as you can prove this, as long as you can prove these heuristics, you don't have to worry about a lot of the most difficult parts of the trace formula. There are no orbital integrals. The count is just going to be up to some lower order term, the Tamagawa number of the group, times the sum over central elements of the group. Now, of course, proving these three heuristics, proving this heuristic that the orbital integrals decay at rate proportional to the dimension of the orbit, you need a little bit more than just the support of the function is shrinking and it's oscillating, right? You need the oscillation to be like exactly along the dimension, like the specific directions that you're taking the orbital integral. So actually proving this heuristic tends to be a lot of work. So this isn't free. This is, again, just an expectation. And when you want to do something rigorously, you have to prove this decay thing. And I don't know, maybe someone who's better at analysis than me knows how to say a very general thing. And I would love if someone could tell me how generally you can actually prove this expectation. But I don't know how to do it besides, again, like specific hacks in each case that you might want to work with. Okay, so that finishes all the discussion of heuristics. Now I'm going to say a little bit about the actual technical details and what goes wrong. So before I do that, let me just ask again, does anyone have any questions? Okay. So basically, the first thing that happens in our non-heuristic real world are like our dream breaks, and in the real world, everything is much more complicated. When the Sadelic quotient isn't compact, then the kernel that we wanted to integrate on the diagonal, the integral doesn't actually converge. So we can't use that to calculate our trace. So what we have to do is we have to truncate this kernel in some way so that its integral does actually converge. And now when you truncate, all the beautiful heuristic, spectral, and geometric expansions, those are going to break because now you're calculating something different that isn't quite the trace, it's some truncated version of the trace. So there are various, there's sort of like a spectrum of particular truncations you can use and various corrections to the truncations. And this gives you like a whole zoo of various versions of the trace formula. And I like to think of this zoo as like lying along a spectrum. There's kind of a coarse expansion, there's a fine expansion, there's an invariant trace formula, there's a stable trace formula. Maybe in the future there'll be a beyond endoscopic trace formula. And the way the spectrum works is that the trace formulas at the top of the spectrum, they're very explicit. There's just like a formula for how to exactly truncate the kernel, and you just try to calculate as much as you can with that truncated kernel. So they're explicit, they're pretty elementary, but the cost of everything is that they have very bad abstract properties. So you might lose like conjugation invariance of the orbital integrals. They might be replaced by some scarier thing that's not conjugation invariant and a giant pain to compute. Conversely, at the bottom of the spectrum, you get trace formulas that are, you get these abstract properties back because you add a bunch of corrections. But these corrections are very, very conceptually and abstractly complicated. And a lot of the corrections they're not even explicit. Like, there'll be like a theorem that there exists a correction that you can add to make this thing invariant. And it won't give a formula for the correction. It'll just be there exists this correction. So these are pretty bad if you want to explicitly calculate something, except because they have these good abstract properties, there are various nice cases in which they simplify very dramatically. And these are even nicer than the things on the top of the spectrum in these nice simple cases. So basically the best way to use the trace formula, or the least painful way to use the trace formula, is to be in one of these nice simple cases where the things near the bottom of the spectrum simplify and use the things near the bottom of the spectrum. Okay, so I think the last thing I'm going to do in this talk is maybe I have a little bit of extra time since we started late, is I'm going to talk about one of sort of my favorite ones of these simple cases. So this is going to be the trace formula for discrete series at infinity. Now these discrete series are coming up again, right? So these discrete series are the things that tell you that something is a modular form for GL2. So automorphic representations with discrete series at infinity, this is a special case, but it's a very good special case. It's not that bad of a special case. So we should talk about these discrete series in general a little bit. So basically, remember back at the beginning of the talk, there's this dictionary about the local components. And these pi infinities basically tell you the qualitative type of an automorphic representation. And what a discrete series is, it's the nicest possible kind of pi infinity. So you should expect that those correspond to kind of the nicest possible kinds of automorphic representations. And on GL2, this is like modular forms vs Moss forms, right? So the modular forms are a lot nicer. So we're going to restrict our attention to these automorphic representations. So what are these discrete series representations? Just as a reminder from our previous talk, these are representations that you can actually realize as L2 functions on the group at infinity. There's a classification result. They're classified into finite subsets of constant size called L packets that, well, we'll denote by this, or we'll also say maybe sometimes you'll see pi discrete of lambda. And the parameter ranges over finite dimensional irreducible representations of the group at infinity. So this is just a real matrix group, and it has finite dimensional representations the way you learn in Lie theory. So just as an example, for G equals GL2 over Q, the L packets are singletons parameterized by a number k greater than or equal to 2, and pi infinity being the sole element of the pi k, It means that it's the weight k discrete series, so it means that pi corresponds to holomorphic modular forms of weight k. So the point is, when you restrict to representations with discrete series at infinity, the invariant trace formula simplifies very dramatically. So here's the actual formula. So we let G over F be some reductive group. We're going to pick a discrete series L packet. We're going to take the set of automorphic representations with the infinite component in the L packet. Then we're going to take a test function on G away from infinity. And what's happening here is we sort of secretly already chose F at infinity to be the pseudo coefficient for this, to be sort of the pseudo coefficient kind of thing for this discrete series L packet, or the sum of pseudo coefficients, right? So there's a little trace against pi infinity of phi lambda, which equals basically 1 if pi infinity is inside the discrete series L packet and 0 otherwise, right? So that's sort of secretly in here because we secretly already picked our test function at infinity. So our freedom is to pick the test function away from infinity. And basically, when you take the sum over traces of all these automorphic representations with the correct component at infinity, we get this particular formula here. Now, I don't think the details of the formula are super relevant to get into now. I just want to emphasize it breaks up into 3 pieces. They're sort of not too much worse than our heuristic formula. So there's some set of conjugacy classes, and there's some like inclusion and exclusion thing going over Levy subgroups, so that's fine. Then there's a volume term, and then there's kind of an orbital integral factored into an infinite place and a finite place. So basically, what's happening here is that this formula, it doesn't make this part any harder than the orbital integral already was. So if you could understand the heuristic trace formula and you can compute all the orbital integrals, then understanding this should be no harder. Like everything you can do where the heuristic trace formula works, you should also be able to do where this discrete at infinity trace formula works. And in fact, it ends up being even better because there's a sort of restriction on the conjugacy classes that you need to sum over. You end up not needing to sum over unipotent conjugacy classes. And in the heuristic trace formula, if you know something about orbital integrals, the unipotent orbital integrals are the worst kinds. So the worst kinds sort of drop out of this formula. So in some sense, you can say that this formula is like even easier than the heuristic formula. So what are some implications of what this lets us do? Well, I think sort of a very good set of example consequences can be found in a paper of Shin and Templier, which sort of push this formula, this Arthur's formula, the simple trace formula, basically as far as people have been able to. And it used it to compute asymptotic statistics of families of automorphic representations with discrete series at infinity. So statistics, what could that mean? Well, first of all, you basically pick this discrete series L packet, you pick some level n, and you count how many automorphic representations there are. You take a limit as n or lambda go to infinity, just as we were discussing before, and you try to figure out what the growth rate is. So this formula was good enough that you don't even get just the main term, you also get an estimate on the error term. Not only do you get these statistics, you can weight these statistics by parameters of the automorphic representations at other places. So basically, because you can pick this weight arbitrarily, you can now talk about equidistribution results of the distribution of this parameter inside this family. Some good applications though are here. So basically, this was able to prove a Sato-Tate equidistribution law, not for a particular automorphic representation, but sort of an average Sato-Tate equidistribution law over all automorphic representations. Satisfying these conditions. And it was also able to show some results on the low-lying zeros of the L functions of automorphic representations in this family on average. So this formula is pretty great. If you do the work and you understand all the orbital integrals, it's not easy work, but it's something that has been done. And then you can get a lot of very nice consequences out of this. So let me skip this next slide. I'm just going to mention that, so on the next talk, what are we going to do? So this is basically like a pretty great thing that the simple case of the invariant trace formula can get us. It lets us understand these discrete series at infinity very nicely. So the next talk is going to discuss sort of, we can go further down the spectrum and we can go beyond the invariant trace formula. And we'll talk about what we can do when we go beyond the invariant trace formula. Like maybe we want other conditions on pi infinity. We don't want to study just discrete series at infinity. Maybe we want to study cohomological representations. So the further down trace formulas will help us do that, and they'll have simplified cases that are nice beyond just discrete series at infinity. Okay, so I think that's everything I had to say today. Thanks everyone for listening, and hope that was understandable.
Yeah, thank you. Thanks a lot for a wonderful talk. Yeah, if any of you have questions. Or comments. Okay, I guess. Yeah, let's thank Rahul again. Yeah, thanks.
Thanks, Rahul, for the nice talk.
Thanks. Let me.
Could you also share the slides of this talk to me?
Yeah. I'll email you the slide. So I'll just reply to the. Yeah, I'll reply to the email with the slides.
Yeah, sure.
Perfect.
Okay.
Let me. Yeah.
Maybe then we can close this session now.
Thanks,
Thank
Surya.
you,
So
Surya,
next
for
time your talk will be on
sharing the
27th,
session.
right?
Sorry?
Oh, sorry.
Your talk will be on 27th, next talk.
Yeah, the second talk will be on.
Okay, then see you.
See you.
Yeah, see you guys. Yeah, thanks.
Let's see.